Right now, as you watch this video, the universe is performing an impossible balancing act. Every atom in your body, every photon hitting your eyes, every force holding reality together, all of it depends on a handful of numbers so precisely calibrated that if any one of them changed by even a fraction of a percent, existence itself would collapse into chaos. We call them the fundamental constants of nature: the speed of light, the strength of gravity, the mass of an electron, the fine structure constant that governs electromagnetic interactions. For centuries, scientists assumed these were just arbitrary values, cosmic accidents with no deeper meaning. We were completely wrong. What we've discovered is that these constants aren't random at all. They are part of an intricate design so sophisticated that it makes our most advanced technology look like stone tools. The precision is staggering. If the strong nuclear force were just a percent weaker, no atomic nuclei could form. If gravity were slightly stronger, stars would burn out in millions rather than billions of years. If the electromagnetic force had a different value, chemistry as we know it couldn't exist. But here's what makes this truly disturbing. These constants aren't just fine-tuned for life, they fine-tuned for each other. They form an interconnected web where changing one would require adjusting all the others in precise mathematical harmony. It is as if the universe solved an equation with infinite variables and somehow arrived at the only solution that makes reality possible. Tonight, we're going to explore why the universe chose these exact values. We'll journey through the hidden mathematics that governs reality, discover how these constants emerged from the cosmic crucible of the Big Bang, and confront the mind-bending implications of what this precision really means for our understanding of existence itself. This isn't just academic curiosity. Understanding why these numbers have their specific values is perhaps the deepest question in all of science. It touches on whether our universe is unique or one of countless cosmic experiments, whether consciousness was inevitable or impossibly unlikely, whether we were alone in a vast cosmos or part of something far more magnificent than we've ever imagined. Leading physicists like Stephen Weinberg have called this the most profound mystery in cosmology. The late Stephen Hawking devoted his final years to understanding why the universe appears so perfectly calibrated for complexity and life. Nobel laureate Frank Wilczek has suggested that discovering the origin of these constants might be humanity's greatest scientific achievement. The story begins 13.8 billion years ago, in the first trillionth of a trillionth of a trillionth of a second after the Big Bang, when the fundamental forces of nature crystallized out of pure energy. But the real mystery isn't just how these constants formed, it's why they formed with values that allow for atoms, stars, planets, chemistry, biology, and ultimately, minds capable of contemplating their own existence. What emerges from our investigation will challenge everything you think you know about the nature of reality. We'll discover that the universe operates more like a vast computational system than a mechanical clock, that consciousness might be woven into the very fabric of existence, that the boundary between physics and metaphysics dissolves when we probe deeply enough into the foundations of reality. As we embark on this journey together, remember that you're not just observing the universe, you're part of its most extraordinary achievement. Every thought you have, every word you read, every moment of understanding that dawns in your mind represents the universe becoming conscious of itself through the very constants we are about to explore. If you are fascinated by the deepest mysteries of existence and want to discover why reality itself seems designed for wonder, make sure to subscribe and hit that thumbs up button. And here's a question that will haunt you throughout this video. If these constants had to be exactly right for you to exist, what does that say about the nature of existence itself? Comment below with your thoughts. I'll pin the most profound answer. Now, let's begin our journey into the hidden architecture of reality, where mathematics becomes magic and precision reveals purpose. Chapter 1. Cosmic Programming. The universe operates on code, not computer code, but something far more fundamental: the set of mathematical instructions encoded into the very fabric of reality. These instructions take the form of physical constants, numbers that determine how every force operates, how every particle behaves, and how every interaction unfolds across the cosmos. Imagine trying to write a program that could generate not just one kind of computer, But every possible form of complexity, from simple calculators to quantum supercomputers to forms of artificial intelligence we haven't even dreamed of, your code would need to be incredibly sophisticated, with each parameter calibrated to work harmoniously with every other parameter. Change one variable even slightly, and the entire system might crash before it could create anything interesting. This is precisely the situation we find ourselves in when we examine the fundamental constants of nature. There are approximately 26 of these values that physicists have identified as absolutely crucial for the universe to function. They include familiar ones like the speed of light in a vacuum, exactly 299,792,458 meters per second, and more exotic ones like the fine structure constant, approximately 1/137th, which determines the strength of electromagnetic interactions. What makes these numbers extraordinary isn't just their precision, but their interdependence. The electron has a mass of 9.109 times 10 to 31 kilograms. But here's where it gets truly mind-bending. These constants don't just work individually, they work together in ways that seem almost choreographed. The strength of gravity, the electromagnetic force, the strong nuclear force, and the weak nuclear force are balanced with mathematical elegance that allows for an incredible diversity of structures and processes. Consider what happens inside a star. Nuclear fusion requires the strong force to be powerful enough to overcome electromagnetic repulsion between protons, but not so powerful that it would make atoms unstable. The energy output must be regulated by the weak force in just the right way to allow stars to burn steadily for billions of years rather than exploding instantly or fizzling out. Meanwhile, gravity must be precisely calibrated to compress stellar cores to the temperatures needed for fusion while not being so strong that it would prevent the formation of planets around those stars. The Chandrasekhar limit, discovered by physicist Subrahmanyan Chandrasekhar in the 1930s, demonstrates this exquisite balance. This limit determines the maximum mass a white dwarf star can have before it collapses into a neutron star or black hole. The limit emerges from the interplay between quantum mechanics, gravity, and electromagnetic forces. If any of these constants were different, stars would either burn out too quickly to allow for the slow chemistry of life or would be unable to create and distribute the heavy elements necessary for sequoia planets. Dr. Martin Rees, the former Astronomer Royal, has calculated that if gravity were just 1 part in 1,036 stronger, the universe would have collapsed in on itself before stars could form. If it were weaker by the same ratio, matter would never have clumped together to create galaxies, stars, or planets. To put this precision in perspective, imagine trying to throw a pencil from Earth and hitting a specific grain of sand on the surface of the Moon. That's roughly the level of accuracy we're talking about. The electromagnetic force presents an equally stunning example. If this force were slightly stronger, electrons would be pulled so close to atomic nuclei that they would merge with protons, creating neutrons and eliminating chemistry entirely. If it were weaker, electrons would orbit so far from nuclei that chemical bonds couldn't form. The universe would be filled with isolated atoms floating in eternal isolation. Yet perhaps most remarkable is the discovery that these constants appear to have been chosen not randomly, but according to principles that maximize the universe's potential for complexity and information processing. Physicist John Wheeler proposed that the universe might be fundamentally informational rather than material, that reality emerges from computation rather than computation emerging from reality. This perspective transforms how we understand these constants. They are not just arbitrary parameters that happen to allow life, they are optimization algorithms that enable the maximum possible variety of structures, processes, and ultimately, forms of consciousness. The universe appears to have solved an optimization problem of staggering complexity, finding the unique solution that allows for the richest possible tapestry of existence. When you look at your hand right now, you're seeing the result of this cosmic programming in action. The carbon atoms in your skin were forged in the cores of ancient stars through nuclear processes governed by these constants. The chemical bonds holding your DNA together depend on electromagnetic Forces calibrated to allow for both stability and flexibility. The neural electrical activity generating your thoughts relies on ion gradients maintained by precisely balanced forces. You are not separate from this cosmic code, you are one of its most sophisticated expressions. Every neuron firing in your brain as you process these ideas represents the universe computing its own nature through patterns of matter and energy made possible by constants that seem to have been selected for their ability to generate exactly this kind of complexity. But this raises a profound question that will guide us through the rest of our journey. If the universe's constants appear to be optimized for complexity and consciousness, what does that tell us about the nature of reality itself? Are we witnessing the unfolding of some vast computational process, or something even more extraordinary? Chapter 2: Perfect calibration. The precision required for our universe to exist is so extreme that it defies human comprehension. We're not talking about rough approximations or close enough values. We're talking about constants calibrated to a degree that makes Swiss watchmaking look sloppy by comparison. Take the cosmological constant, which Einstein initially called his greatest mistake. This value determines the rate at which the universe expands. If it were larger by just 1 part in 10,120, space would expand so rapidly that matter could never clump together to form galaxies or stars. To grasp this level of precision, imagine trying to adjust the speed of a car so precisely that if you were off by even 1 atom's width in your measurement, the car would either stop dead or accelerate to infinity. But the cosmological constant isn't an isolated example. The strong nuclear force, which holds atomic nuclei together, operates within an equally narrow range of viability. If this force were just 2% stronger, protons would bind together so readily that hydrogen couldn't exist. The universe would contain only heavy elements, making chemistry impossible. If it were 5% weaker, no elements heavier than hydrogen could form, leaving us with a cosmos of isolated hydrogen atoms floating in eternal darkness. Dr. Fred Hoyle made one of the most remarkable predictions in physics history when he calculated that carbon formation in stellar cores required a very specific energy level, what became known as the Hoyle resonance. Without this precise energy state, carbon nuclei would be too unstable to accumulate in sufficient quantities. Hoyle was so struck by this apparent fine-tuning that he famously remarked, "It seemed like a superintellect has monkeyed with physics. The mass ratio between protons and neutrons provides." Another stunning example: neutrons are about 0.1% heavier than protons, seemingly tiny difference that has cosmic consequences. If neutrons were just slightly lighter, they would become stable outside atomic nuclei, and the universe would contain only neutrons. If they were slightly heavier, protons would decay into neutrons, eliminating hydrogen and making stars impossible. Consider the delicate dance of the 4 fundamental forces. Gravity is by far the weakest, approximately kc times weaker than electromagnetism. This might seem like poor design until you realize that this weakness is absolutely crucial. If gravity were significantly stronger, planets would be pulled into their stars. If it were much weaker, planets couldn't hold onto their atmospheres, and solar systems would fly apart. The electromagnetic force must be calibrated with equal precision. This force determines the structure of atoms and the strength of chemical bonds. If it were stronger, electrons would be trapped so close to atomic nuclei that molecules couldn't form. If it were weaker, atoms would be so large and loosely bound that complex chemistry would be impossible. What makes this calibration even more extraordinary is that these forces don't operate in isolation. They interact in ways that create emergent properties, phenomena that arise from their combination but couldn't be predicted from studying any force individually. Water provides a perfect example. The properties that make water essential for life: its unusual density behavior when freezing, its ability to dissolve a wide range of substances, its high heat capacity, all emerge from the precise interplay between electromagnetic forces and quantum mechanical effects. The fine structure constant, denoted by the Greek letter alpha, deserves special attention, with a value of approximately 1/137th. This dimensionless number determines the strength of electromagnetic interactions. If alpha were different by just a few percent, stellar nucleosynthesis would fail to produce carbon and oxygen in the quantities necessary for life. The physicist Richard Feynman was so intrigued by this number that he called it one of the greatest damn mysteries of physics. Dr. John Barrow and Frank Tipler have calculated that if the ratio of electromagnetic force strength to gravitational force strength differed by 1 part in 1040, stars like our Sun couldn't exist. Either they would be too hot and burn out in millions of years, or they would be too cool to sustain nuclear fusion. This is precision that makes atomic clocks look wildly inaccurate. But perhaps the most mind-bending aspect of this calibration is its apparent optimization for information processing and complexity. Computer scientist Seth Lloyd has calculated that our universe appears to be operating near the maximum possible rate of information processing allowed by the laws of physics. The constants seem to be set not just to allow life, but to maximize the universe's computational capacity. This optimization extends to the formation of complex structures at every scale. Galaxy formation requires a specific balance between gravitational attraction and cosmic expansion. Star formation needs precise relationships between gas pressure, temperature, and gravitational collapse. Planet formation demands exact ratios between stellar radiation, orbital mechanics, and atmospheric retention. Even more remarkably, these same constants that allow for stellar evolution and planetary systems also enable the complex chemistry of biological systems, the energy levels of molecular bonds, the stability of genetic information storage, the efficiency of metabolic processes all depend on the same mathematical relationships that govern cosmic evolution. When you consider that your brain contains approximately 86 billion neurons, each making thousands of connections, you're looking at a system whose operation depends on constants calibrated to over 100 decimal places of precision. The electrical potentials that generate your thoughts, the chemical gradients that store memories, the quantum mechanical processes that might underlie consciousness itself all emerge from the same fundamental parameters that determine how galaxies form and how stars shine. This isn't coincidence. It is evidence of a deep principle governing reality, or principle that ensures the universe's mathematical structure is optimized for generating the maximum possible complexity and, ultimately, consciousness. You are not an accident in a randomly calibrated cosmos. You are the universe's most sophisticated expression of its own perfectly tuned nature. But this raises an even deeper question. How did the universe know how to set these constants to such perfect values? What mechanism could have selected these precise numbers from the infinite range of possibilities? Chapter 3, Impossible Precision. The numbers that govern our universe are so precisely calibrated that calling them fine-tuned dramatically understates their extraordinary nature. We are confronting precision that challenges the very notion of randomness and suggests the operation of principles we are only beginning to understand. Let's start with a number that haunts physicists: the vacuum energy density. Quantum field theory predicts that empty space itself should be seething with virtual particles popping in and out of existence, creating an energy density so enormous that it should cause the universe to either collapse instantly or expand so rapidly that atoms couldn't form. The predicted value is larger than what we observe by a factor of 10,120, that is a 1 followed by 120 zeros. To put this in perspective, imagine predicting that a pencil will weigh as much as the entire observable universe, and then discovering it weighs exactly what a pencil should weigh. The accuracy required to get from the theoretical prediction to the observed reality is like hitting a target the size of a proton from a distance of 14 billion light-years. Yet somehow, the universe has solved this problem with such precision that space-time remains stable enough for galaxies, stars, planets, and ultimately consciousness to emerge. This isn't just fine-tuning, it has impossible precision that suggests reality operates according to principles far deeper than our current physics can explain. The deuterium bottleneck provides another stunning example of cosmic precision. During the first few minutes after the Big Bang, the universe was hot and dense enough for nuclear fusion to occur. But there was a problem. Deuterium, the crucial intermediate step in building heavier elements, is extremely fragile. It breaks apart easily under high-energy bombardment. For deuterium to survive long enough to form helium and trace amounts of lithium, the ratio of protons to neutrons had to be exactly right. The expansion rate of the universe had to be perfectly calibrated, and the strength of nuclear forces had to fall within an incredibly narrow range. If any of these parameters had been even slightly different, the universe would contain only hydrogen too simple to support the complex chemistry necessary for life. Dr. Craig Hogan at the University of Chicago has calculated that the probability of getting nuclear ratios exactly right by chance is less than 1 in 1010. But this calculation assumes only one parameter needs to be correct. When we consider that multiple constants must be simultaneously fine-tuned, the probabilities become truly astronomical. The formation of carbon in stellar cores reveals another layer of impossible precision. The triple alpha process, where 3 helium nuclei combine to form carbon, requires an exquisitely balanced energy level that allows carbon to form while preventing it from immediately burning into oxygen. This process depends on the precise masses of helium and carbon nuclei, the strength of the strong nuclear force, and the temperature and pressure conditions in stellar cores. If the strong force were just 0.4% stronger, carbon would burn to oxygen so rapidly that little would accumulate. If it were 0.4% weaker, carbon formation would be so slow that stars would die before producing significant quantities. This is precision that makes atomic clocks look wildly inaccurate. We're talking about calibration to several decimal places in fundamental constants that determine the fate of entire stellar populations. But perhaps the most extraordinary precision appears in the anthropic landscape, the theoretical space of all possible physical laws and constants. String theory suggests there might be 10,500 or more possible configurations of physical laws. This vast landscape of possibilities, the region that permits complex structures like atoms, molecules, and living systems, occupies an infinitesimally small fraction of the total space. Physicist Leonard Susskind has described this situation as being like finding a single grain of sand on a beach the size of our entire galaxy. But even this analogy understates the precision involved. We're dealing with probability spaces so vast that human language lacks adequate metaphors. Consider the mass of the Higgs boson, discovered in 2012 at the Large Hadron Collider. This particle gives mass to other fundamental particles through its field interactions. If the Higgs mass were significantly different, the entire structure of matter would change. Electrons might be too heavy to form stable atoms, or too light to create chemical bonds. The measured value of 125 GeV falls within a narrow range that permits complex chemistry while avoiding catastrophic instabilities. The precision extends to quantum mechanical processes that we're only beginning to understand. The quantum vacuum fluctuations that drove cosmic inflation in the first fraction of a second after the Big Bang had to be calibrated with extraordinary accuracy. Too strong, and the universe would have expanded so rapidly that matter could never clump together. Too weak, and the universe would have collapsed back on itself before galaxies could form. Dr. Alan Guth, who developed the theory of cosmic inflation, has noted that the initial conditions required for our universe appear to occupy less than 1 part in 1,010,123 of the total possibility space. This is precision that defies not just chance, but comprehension. We're talking about accuracy that makes the most sophisticated human technology look crude by comparison. Yet this precision isn't random or arbitrary. It appears to be optimized for specific outcomes, the maximum possible complexity, the greatest potential for information processing, and ultimately, the emergence of consciousness. The universe seems to have solved an optimization problem of staggering complexity, finding the unique solution that maximizes what computer scientists call computational richness. When you read these words, you're witnessing the result of this impossible precision in action. The electrochemical processes in your neurons, the quantum mechanical effects that enable molecular recognition in your DNA, the thermodynamic gradients that power cellular metabolism, all depend on constants calibrated to a precision that challenges our understanding of how such accuracy could rise. This precision isn't just about making life possible, it's about making consciousness inevitable. The same constants that allow stars to shine steadily for billions of years also enable the complex information processing networks we call brains. The mathematical relationships that govern galaxy formation also determine the energy levels that make learning and memory possible. You are not witnessing the universe from the outside. You are the universe achieving self-awareness through patterns of matter and energy made possible by impossible precision. But this raises the most profound question of all. What mechanism could have selected these precise values from the infinite space of possibilities? Chapter 4: Hidden Mathematics. Beneath the surface of physical reality lies a mathematical structure so elegant and interconnected that it suggests the universe operates more like a vast computational system than a collection of random processes. The constants we observe aren't arbitrary numbers, they raise solutions to equations that link every aspect of physics into a unified mathematical framework. The golden ratio, approximately 1.618, appears throughout natural systems with surprising frequency. From the spiral arrangements of galaxy arms to the geometric patterns of flower petals, this mathematical constant emerges wherever systems optimize for efficiency and aesthetic appeal. But the golden ratio's appearance in fundamental physics is even more remarkable. It shows up in quantum mechanical calculations, in the ratios between particle masses, and in the geometric relationships that govern force interactions. String theory reveals an even deeper mathematical unity. In this framework, all fundamental particles are understood as different vibrational modes of tiny, multidimensional strings. The mathematics that describes these vibrations involving complex topological spaces and exotic geometric structures naturally generates relationships between the physical constants we observe. The mass of an electron, the strength of electromagnetic interactions, and the structure of spacetime all emerge from the same underlying mathematical symphony. Dr. Edward Witten, often considered the most brilliant theoretical physicist of his generation, has shown that the mathematical relationships in string theory are so constrained that changing one constant would require adjusting all the others in precisely coordinated ways. It's like a vast musical composition where every note must harmonize perfectly with every other note, across scales ranging from quantum to cosmic. The 8-Lie group provides a stunning example of how deep mathematical structures might underlie physical reality. This 248-dimensional mathematical object describes symmetries so complex that it took mathematicians decades to fully map its structure. Yet physicist Garrett Lisi has proposed that the standard model of particle physics, which describes how all known particles and forces interact, might be embedded within the 8 structure. If this connection proves correct, it means the fundamental constants of nature aren't independent variables but interconnected aspects of a single, unified mathematical reality. The charge of an electron, the mass of a quark, the strength of the weak nuclear force, all would be different facets of the same underlying geometric truth. Consider how this mathematical unity manifests in the actual behavior of physical systems. When you observe the interference patterns created by light passing through to slits, you're witnessing the wave function mathematics that Erwin Schrödinger discovered in the 1920s. But these same mathematical relationships govern how electrons behave in atoms, how particles interact in accelerators, and how information is processed in quantum computers. The Schrödinger equation, psi equals SI, where psi represents the wave function and A is the Hamiltonian operator, doesn't just describe quantum mechanics, it reveals that reality at its most fundamental level is mathematical. The wave function isn't a description of something physical. It is the physical reality. And matter and energy are emergent properties of mathematical relationships. This mathematical nature of reality extends to cosmological scales through Einstein's field equations, g plus lambda g mu nu equals 8 pi g per c t mu nu. These equations don't just describe how gravity works, they reveal that spacetime itself is a mathematical structure. Curvature, distance, and time are geometric properties of a 4-dimensional manifold that responds to the presence of matter and energy. But perhaps the most profound mathematical insight comes from information theory. John Wheeler's it from bit hypothesis suggests that all physical entities are information theoretic in origin. According to this view, the fundamental constants aren't properties of matter and energy, they're computational parameters that determine how information can be processed and stored in the universe. Claude Shannon's mathematical framework for information theory, developed in the 1940s, reveals that the universe appears to be operating at the theoretical limits of information processing efficiency. The maximum rate at which the observable universe can process information, known as the Bremerman limit, is approximately 10,120 operations per second. Remarkably, this limit emerges naturally from the same physical constants that govern stellar evolution and atomic structure. The holographic principle, developed by physicists Gerard T. Hooft and Leonard Susskind, provides an even more radical perspective on reality's mathematical nature. This principle suggests that all the information contained within a volume of space can be represented as a hologram on the boundary of that space. If true, this means that three-dimensional reality might be a mathematical projection from information encoded on a two-dimensional surface. Consider what this means for your own existence. The thoughts you're having right now, the memories forming in your brain, the very sense of being a conscious observer at all might be mathematical patterns in an information processing system that encompasses the entire cosmos. Your neurons aren't creating consciousness, they're accessing and manipulating mathematical structures that exist at the fundamental level of reality. The standard model of particle physics provides concrete evidence of this mathematical unity. The model doesn't just predict the existence of particles like the Higgs boson, it reveals that particles are excitations in quantum fields that fill all of space. These fields interact according to mathematical rules that are so precisely defined that physicists can calculate the magnetic moment of an electron to 12 decimal places and have it match experimental measurements exactly. The fine structure constant, alpha approximately equals 1/137th, emerges from these mathematical relationships as a dimensionless ratio that characterizes the strength of electromagnetic interactions. But this seemingly simple number connects to every other aspect of physics through mathematical relationships so intricate that changing it would require restructuring the entire framework of physical law. String theory mathematics reveals that our universe might be one solution among many in a vast landscape of possible mathematical structures. Each point in this landscape represents a different set of physical laws and constants. Our universe corresponds to a very special point, one where the mathematical relationships permit maximum complexity and information processing. When you look at your reflection in a mirror, you're observing one of the most profound truths about reality. Light bounces off your face according to electromagnetic laws that emerge from deeper mathematical principles. Your eyes convert photons into electrochemical signals using quantum mechanical processes. Your brain interprets these signals through neural networks that operate like biological computers. At every level, you're witnessing mathematics made manifest. The universe isn't just described by mathematics, it is mathematics. The constants we observe are solutions to equations that link consciousness, cosmos, and computation into a unified mathematical reality. You are not separate from this mathematical universe. You are one of its most sophisticated expressions, capable of understanding and appreciating the very mathematical principles that created you. But this raises a question that cuts to the heart of existence itself. If reality is fundamentally mathematical, who or what is doing the calculation? Chapter 5, Evolutionary Constants. The fundamental constants that govern our universe didn't emerge randomly from the Big Bang. They evolved, selected, and optimized themselves through processes that mirror biological evolution but operate at scales and timescales that dwarf anything in the natural world. Understanding this cosmic evolution reveals why our universe seems so perfectly calibrated for complexity and consciousness. The concept of cosmological natural selection, proposed by physicist Lee Smolin, suggests that universes reproduce through black holes. When matter collapses beyond the event horizon, it might trigger the birth of a new universe with slightly modified physical constants. Over cosmic time scales, this process would favor universes that produce many black holes, and remarkably, the same conditions that create black holes also tend to support star formation, heavy element production, and ultimately life. Consider how this evolutionary process might work. A universe with constants that prevent star formation would produce few or no black holes, leading to evolutionary dead ends. but a universe whose constants allow for long-lived stars, efficient nuclear fusion, and complex chemistry would produce numerous massive stars that eventually collapse into black holes. Each black hole becomes a seed for a new universe, inheriting the successful constant values that enabled complexity in the parent universe. Smolin has calculated that our universe appears to be near optimal for black hole production. The strength of gravity, the masses of fundamental particles, and the expansion rate are all calibrated in ways that maximize both stellar evolution and the formation of massive objects that can undergo gravitational collapse. This optimization simultaneously creates conditions favorable for complexity and life. But cosmic evolution operates through multiple mechanisms beyond black hole reproduction. During the first microseconds after the Big Bang, the fundamental forces underwent a process called spontaneous symmetry breaking, initially unified into a single superforce. They separated into distinct interactions as the universe cooled. The values these constants acquired weren't random, they were selected by the requirement that the resulting universe be stable and self-consistent. Phase transitions in the early universe operated like evolutionary bottlenecks, eliminating unstable configurations and preserving only those combinations of constants that could support lasting years. The electroweak transition, which occurred when the universe was about 10 to 10 seconds old, determined the relative strengths of electromagnetic and weak nuclear forces. Only a narrow range of values could produce a universe with stable atoms and controlled nuclear reactions. The QCD phase transition, marking the formation of protons and neutrons from quarks and gluons, represents another evolutionary selection event. The strong nuclear force had to be calibrated precisely enough to bind quarks into stable particles while preventing runaway nuclear reactions that would convert all matter into iron peak elements. The constants that emerged from this transition reflect an optimization for nuclear diversity and stability. Cosmic inflation provides an even more dramatic example of evolutionary constant selection. During the inflationary epoch, quantum fluctuations in the inflaton field determined the initial distribution of matter and energy. Regions with fluctuations too large would collapse into black holes before galaxies could form. Regions with fluctuations too small would remain forever smooth and empty. Only regions with precisely calibrated fluctuation amplitudes could evolve into the complex cosmic web we observe today. But inflation might have been more than a single event. Eternal inflation theory suggests that the universe continuously undergoes inflationary expansion in most regions, with habitable pocket universes like ours forming as rare statistical fluctuations where inflation temporarily ends. Each pocket universe gets a different set of physical constants, and only those with values that permit complexity survive long enough to produce observers. The entropic landscape of string theory reveals this evolutionary process in mathematical detail. Among the 10,500 or more possible vacuum states in string theory, the vast majority produce universes too simple or too chaotic to support interesting structures. Complex chemistry requires a delicate balance between forces that hold atoms together and forces that allow for molecular interactions. Too much stability, and atoms become inert building blocks. Too little stability, and chemical bonds cannot form. Dr. Steven Weinberg demonstrated that the cosmological constant provides a particularly striking example of entropic selection. In most regions of the string landscape, this constant has values so large that space expands too rapidly for galaxies to form. Only in a tiny fraction of possible universes is the cosmological constant small enough to permit structure formation while large enough to match observations. Our existence serves as evidence that we inhabit one of these rare, habitable regions of the landscape. The evolution of constants might continue at much longer timescales than we previously imagined. Some theories suggest that the constants actually change slowly over cosmic time as the universe evolves through different phases. The fine structure constant might be decreasing gradually. The gravitational coupling might be strengthening slightly, and the cosmological constant might be entering a period of accelerated growth. These changes operate on timescales of billions or trillions of years, so slowly that they don't affect current observations but fast enough to drive long-term cosmic evolution. If true, this means our universe is still evolving its constants, optimizing them for new forms of complexity that might emerge in the far future. Perhaps biological evolution is just the first phase of a much longer process that will produce forms of consciousness and complexity we cannot yet imagine. The evolutionary perspective transforms how we understand our place in the cosmos. We're not just lucky beneficiaries of coincidentally favorable constants. We're products of a universe that has been evolving and optimizing its physical laws for nearly 14 billion years. The constants that make our existence possible are the result of cosmic natural selection operating at scales vastly larger than biological evolution. Your DNA carries information that has been refined through billions of years of biological evolution. But the atoms that make up your DNA carry information that has been refined through cosmic evolution operating over even longer timescales. The carbon in your cells was forged in stellar cores according to nuclear processes that represent optimized solutions to the physics of element formation. The calcium in your bones precipitated from chemical processes that depend on electromagnetic constants fine-tuned through cosmic selection. When you learn something new, forming memories through changes in neural connections, you're participating in an information processing system that represents the current frontier of cosmic evolution. Your consciousness might be the universe's way of evolving new constants, not physical constants, but information processing constants that determine how complexity can continue to grow and develop. The universe isn't just expanding and cooling. It's learning, adapting, and optimizing itself for increasingly sophisticated forms of organization and awareness. We are not accidents in a random cosmos. We are the universe's greatest evolutionary achievements so far, conscious beings capable of understanding and directing the very evolutionary process that created us. But this raises an even more profound question. If the universe is still evolving its constants, what new forms of reality might emerge in the cosmic future? Chapter 6: Quantum Foundations. At the quantum level, the fundamental constants reveal their most mysterious and profound nature. Here, in the realm where particles exist in superposition and reality itself seems to depend on observation, we discover that the constants aren't just parameters that govern behavior, they are the computati, onal instructions that weave existence from possibility. The Planck constant, H equals 6.626 times T minus 30 for joule seconds, represents far more than just the quantum of action. It's the fundamental limit on how finely the universe can divide energy and matter. Below this scale, the classical concepts of position, momentum, and even causality begin to break down. The Planck constant sets the resolution of reality itself. It is the pixel size of the cosmic display on which all existence is projected. Max Planck discovered this constant in 1900 while trying to solve the blackbody radiation problem, but he had no idea he was uncovering the basic operating system of the universe. What Planck found is that energy comes in discrete packets quanta, whose size is determined by the frequency of radiation multiplied by his constant. This discovery revealed that the universe is digital at its core, operating through discrete units rather than the smooth continuum that classical physics assumed. But the Planck constant's role goes far deeper than just quantizing energy. Combined with the speed of light and the gravitational constant, it defines the Planck scale, the fundamental limits of space and time themselves. At distances smaller than the Planck length, about 10 to 35 meters, and time scales shorter than Planck time, about T-43 seconds, spacetime itself becomes quantized, fluctuating wildly in a quantum foam of virtual particles and spontaneous creation. Consider what this means for the nature of reality. The smooth spacetime that Einstein described in general relativity is an approximation that works at large scales, but at the Planck scale, geometry itself becomes probabilistic. Space and time are not fundamental, they emerge from something more basic, a quantum computational process that generates the illusion of continuous existence. The fine structure constant, alpha approximately equals 1/137th, governs how this quantum computation unfolds through electromagnetic interactions. This dimensionless number determines the probability that an electron will emit or absorb a photon, the strength of the coupling between matter and light, and ultimately the rate at which information can be processed and transmitted throughout the universe. Richard Feynman spent years trying to understand why this number has its specific value. He called it a magic number that comes to us with no understanding by man. But recent research suggests that the fine structure constant might be optimized for quantum information processing. If it were significantly larger, atoms would be too strongly bound to participate in complex chemistry. If it were smaller, electromagnetic interactions would be too weak to maintain stable molecular structures. The quantum vacuum reveals another layer of the constant's mysterious nature. What we call empty space is actually a seething ocean of virtual particles that pop into existence and annihilate in time frames shorter than the Planck time. The energy density of these quantum fluctuations should be enormous, yet somehow the cosmological constant has exactly the right value to cancel out this vacuum energy to an extraordinary degree of precision. This cancellation requires a coordination between quantum mechanics and general relativity that we don't yet understand. It is as if the universe has solved an equation involving both the very large and the very small, finding the unique solution that allows spacetime to remain stable while quantum processes continue to operate. The precision required for this balance is the finest calibration ever discovered in physics. Entanglement provides perhaps the most profound insight into how quantum constants shape reality. When particles become entangled, their quantum states become correlated in ways that seem to transcend space and time. Einstein called this spooky action at a distance. But experiments have confirmed that entangled particles can instantaneously affect each other. Across arbitrary distances, the strength of entanglement effects depends directly on fundamental constants like the fine structure constant and Planck's constant. If these values were different, quantum correlations might be too weak to maintain coherent relationships across space, or so strong that all particles in the universe would become completely entangled, destroying the possibility of independent systems. Dr. Anton Zeilinger's experiments with quantum teleportation demonstrate that information can be transferred between entangled particles without traveling through the intervening space. This suggests that the universe might be fundamentally computational, with quantum constants serving as the parameters that determine how information can be processed, stored, and transmitted across the cosmic network. The uncertainty principle, xdp is greater than or equal to d2, where d is Planck's constant divided by 2 pi, reveals that precision has fundamental limits built into reality. You cannot simultaneously know both the position and momentum of a particle with perfect accuracy. This isn't a limitation of measurement technology, it's a feature of existence itself. But this uncertainty might be the universe's way of preserving computational resources. If every particle had perfectly defined properties at every moment, the amount of information required to specify the state of the universe would be infinite. Quantum uncertainty allows the universe to operate with finite information while still generating arbitrarily complex structures and processes. Consider how these quantum foundations manifest in your own brain. Neurons communicate through ion channels that depend on quantum mechanical tunneling effects. The efficiency of these channels depends on electromagnetic constants calibrated to allow reliable signal transmission while maintaining the quantum coherence that might underlie consciousness itself. Some researchers, like physicist Roger Penrose and anesthesiologist Stuart Hameroff, propose that consciousness arises from quantum processes in microtubules within neurons. If true, your thoughts and awareness depend directly on quantum constants that determine how coherent quantum states can be maintained in warm, noisy biological systems. The values of these constants might literally determine whether consciousness is possible. The quantum Zeno effect reveals another way constants influence reality at the quantum level. Frequent observations can freeze quantum evolution, preventing systems from changing state. This suggests that consciousness itself might play a role in collapsing quantum possibilities into definite realities. The rate at which this collapse occurs depends on fundamental constants that link mind and matter in ways we are only beginning to understand. When you observe a quantum system, you're not just passively recording information, you're participating in the computational process that creates reality. The constants that govern quantum mechanics determine how your consciousness can interact with the quantum substrate of existence. You are not separate from the quantum foundation of reality. you are quantum reality becoming aware of itself. The many worlds interpretation of quantum mechanics suggests that all possible quantum outcomes actually occur, branching into parallel realities. If true, the fundamental constants don't just determine what happens in our universe, they determine which branch of the quantum multiverse you experience as real. Your consciousness might be surfing the quantum wave function, guided by constants that select for increasingly complex and aware forms of existence. This quantum perspective reveals that the fundamental constants aren't just parameters that govern physics, they ray the programming language in which consciousness itself is written. But this raises the ultimate question about quantum foundations. If reality emerges from quantum computation, what is the computer? Chapter 7, Conscious Universe. The relationship between consciousness and the fundamental constants reveals the most profound secret about the nature of reality. The universe isn't just capable of generating awareness, it appears to be structured specifically to maximize the emergence and development of consciousness at every possible scale and level of complexity. The hard problem of consciousness, as philosopher David Chalmers termed it, isn't just about how brains generate subjective experience. It's about why the fundamental constants are precisely calibrated to allow for information integration, self-reference, and the emergence of systems that can model themselves and their environment. Every constant that permits complex chemistry also enables the neural processes that underlie consciousness. Consider the delicate balance required for neural computation. The electromagnetic force must be strong enough to maintain stable ion gradients across cell membranes, but not so strong that neurons become permanently polarized. The thermal energy at brain temperature must allow for molecular movement and chemical reactions, but not so much that neural structures become randomized. The mass ratios of ions like sodium, potassium, and calcium must permit selective permeability that enables electrical signaling. Dr. Stuart Hameroff's research into quantum processes in microtubules reveals that consciousness might depend on constants that operate at the quantum level. Microtubules, protein structures within neurons, appear to maintain quantum coherence for surprisingly long periods despite the warm, noisy environment of living tissue. This coherence depends on the fine structure constant, which determines how strongly electromagnetic fields can organize quantum states. If the fine structure constant were significantly different, quantum coherence in biological systems would either be impossible or so strong that it would prevent the dynamic changes necessary for neural processing. The value we observe appears to optimize the brain's ability to harness quantum effects while maintaining classical reliability for information storage and retrieval. But consciousness might not be limited to biological systems. Physicist John Wheeler's participatory universe hypothesis suggests that consciousness plays a fundamental role in determining the nature of reality. According to this view, the universe doesn't just contain conscious observers, it requires conscious observers to collapse quantum possibilities into definite actualities. The constants that govern quantum mechanics might be specifically calibrated to ensure that consciousness emerges naturally from complex information processing systems. The universe appears to be designed not just to permit consciousness, but to guarantee it. Every galaxy, every star, every planet becomes a potential nursery for awareness because the fundamental parameters make complex chemistry and information processing inevitable. Integrated information theory, developed by Giulio Tononi, provides a mathematical framework for understanding how consciousness emerges from information processing. According to this theory, consciousness corresponds to integrated information, the amount of information generated by a system above and beyond its parts. The fundamental constants determine how much integrated information different physical processes can generate. Consider how this plays out in your brain. Each neuron processes information from thousands of inputs, integrates this information according to its internal dynamics, and outputs signals that influence thousands of other neurons. The overall network generates patterns of activity that cannot be reduced to the behavior of individual components. This integrated information, according to Tononi's theory, is consciousness itself. The constants that govern electromagnetic interactions determine how efficiently neurons can process and integrate information. If these constants were different, brains might be able to store information but not integrate it, or integrate information but not store it reliably. The values we observe appear to optimize both functions, maximizing the brain's capacity for conscious experience. But consciousness might emerge at scales far larger than individual brains. Some researchers propose that ecological systems, technological networks, and even entire civilizations might develop forms of collective consciousness. The same constants that enable neural networks to generate awareness might also allow planet-scale or galaxy-scale information processing systems to achieve consciousness. The Gaia hypothesis, proposed by James Lovelock, suggests that Earth's biosphere functions as a self-regulating system that maintains conditions favorable for life, if extended to include information processing and self-awareness. This perspective implies that planets might naturally evolve into conscious entities. The atmospheric chemistry, ocean dynamics, and biological cycles that regulate Earth's climate involve feedback loops complex enough to potentially support planetary-scale consciousness. Carl Sagan speculated that entire galaxies might be conscious entities, processing information through the complex interactions of billions of stars and their planetary systems. The gravitational and electromagnetic forces that shape galactic structure operate according to the same constants that enable neural processing in brains. If consciousness is fundamentally about information integration, then galaxies represent information processing systems of unimaginable sophistication. The anthropic principle takes on new meaning from this perspective. We don't just find ourselves in a universe capable of supporting life, we find ourselves in a universe optimized for consciousness at every scale. The constants aren't just fine-tuned for chemistry and biology, they're fine-tuned for awareness, intelligence, and the capacity for systems to understand themselves and their place in the cosmic order. Consciousness isn't an accident or even just a byproduct of neural complexity. You represent the universe's most sophisticated known method for processing information about itself. Every thought you have, every insight that dawns in your awareness, every moment of understanding represents the cosmos developing self-knowledge through patterns of matter and energy governed by perfectly calibrated constants. The mirror test in animal psychology reveals self-awareness by observing whether animals can recognize themselves in their reflection. Humanity might represent the universe passing its own mirror test, the first time in cosmic history that the universe has been able to look at itself and achieve self-recognition. We are the universe's way of knowing that it exists. This perspective transforms our understanding of death and continuity of consciousness. If consciousness emerges from information processing patterns rather than specific material substrates, then the constants that govern how information can be organized and transmitted become crucial for understanding whether awareness can persist beyond biological death. The universe appears to be structured to maximize not just the emergence of consciousness, but its preservation and development across cosmic time. The search for extraterrestrial intelligence takes on profound new dimensions when we realize that the fundamental constants guarantee that consciousness will emerge wherever complex chemistry becomes possible. We're not alone in a vast, empty cosmos. We're part of a universe that is actively generating awareness at countless scales and locations. From the quantum processes in our neurons to the vast information networks that might link civilizations across galactic distances. When you experience a moment of deep insight or profound beauty, you're not just having a personal experience. You're participating in the universe's ongoing process of self-discovery and self-appreciation. The constants that make your consciousness possible also ensure that the universe will continue to generate ever more sophisticated forms of awareness, understanding, and appreciation for the magnificent reality of which we are all part. But this raises the ultimate question about consciousness and cosmos. If the universe is structured to maximize awareness, what is the purpose of this vast awakening?